I'd like to hear from you about the unit test. Yay, nay? Yeah?
Still don't think I get carbocation.
Okay. I. Wait, tell me more. What was hard about it on active?
There was a question that you didn't ask for Lewis for lone pairs in the instructions.
Oh.
I expected you to put them.
No, that is terrible.
That was one of the 3 guards.
And the feedback on it will have nothing to do with lone pairs.
No.
I know it. I know it. The
only reason we figured that out is because I was like crashing out on the group chat to Andy. Andy was like, "Hey, try putting the lone pairs."
I hear you. Active is very finicky about that. And that's one thing that I would like for them to change. In fact, that's something that I should maybe make note of. I had this realization the other day that I kind of am a businessman. Like when it comes to your education, I've chosen a company to partner with. And that impacts you more than it impacts me. And so I like had this realization of how important it is that I'm thoughtful of who I partner with for homework because that impacts my students. And I will say I didn't pick active willy-nilly. Active was designed by a chemist for chemists. And a lot of its features are way more student-friendly, user-intuitive than a lot of other online homework platforms. I actually sat in on like 4 different companies, like homework platform companies. And Active was the one that I felt gave the best price and the best resources. But they could still be better.
Yeah, I mean, this was certainly, like, up until this point, they haven't been that bad. There's always been 1 or 2 really hard ones in each question, which is cool, but, like, this one was just something else.
You can see the text, you can scream.
I believe it. So Aiden, you said that you are still struggling to understand carbocations. What can you narrow in on your question of what it is?
So the question was which of the following carbocations is expected to proceed through a carbocation rearrangement. And so there's one where the cation is on a secondary carbon adjacent to a tertiary carbon. So I was like, okay, that one definitely. But then it says that there's another one where it's on a secondary carbon adjacent to a quaternary carbon. And it says that that one would go for one as well.
Do you have the question pulled up?
Yeah.
Can you read it again verbatim?
Which of the following carbocations is expected to proceed through a carbocation rearrangement?
That's all it says. Because there are actually different versions of this. Where do you see the quaternary? Oh, and the correct answer is C.
Yes. So I'm confused why that one works, I guess.
Okay.
Or why that would go through
I misunderstood your question.
Sorry, no, I.
So we have kind of 2 situations like this. Secondary carbocation adjacent to a tertiary carbon. Secondary carbocation adjacent to a quaternary carbon. What is the goal of a carbocation rearrangement? Or what thermodynamic benefit is there to a carbocation rearrangement?
In my mind, it's just that you want the cation to be on a more substituted carbon.
That's right.
Can you still put one on a carbon that has all?
No.
Oh, okay.
You can't put it on here because that has 4 bonds. And you can't put it on here because that has 4 bonds. But you do want something more substituted. So in the case of a tertiary carbon, a hydrogen can shift over. Well, hydrogen with its electrons is H-, so we call that hydride shift. This quaternary carbon has no hydrogens. So the only thing I could move would be an entire methyl group. So I'll take that methyl group and I'll shift it over. That still leaves me with a more substituted carbon. It goes from quaternary to tertiary, but a tertiary carbocation is more stable than a secondary carbocation.
So it can still happen if you're moving a methyl group, it's just less common.
It's less common. One, we run into it less often. And two, it takes a lot more energy. So for instance, if this molecule or this carbocation had been between a quaternary carbon and a tertiary carbon, it takes much less energy to move a hydride for the same gain, a tertiary carbocation. So it would rearrange to this position. The term carbocation rearrangement does give students this false impression that the carbocation moves. Now, I didn't have any of you show me mechanisms where we had a carbocation rearrangement, but when I do show those, oftentimes I get this arrow. Students start from the positive charge and point to where it ends up. But what is this arrow called? An electron arrow. What electrons are moving? The hydride's electrons. So if you want to show how electrons move, you don't start from a positive charge. You go towards a positive charge. And to the point of strange rearrangements, this carbocation rearranges as well. But it doesn't rearrange for the sake of a more stable carbocation. It rearranges for the sake of ring strain. Remember that rings less than 6 members have compressed angles in their bonds. 5 is somewhat stable, but 4 and 3-membered rings are very unstable. So anything they can do to expand their bond angles, they will do. So for instance, here we'll see a bond between these 2 carbons shift to this tertiary carbocation. If I were to number these groups, what I'd be saying is that 2 and 5 stop bonding to each other, but 1 and 5 start bonding to each other. That gives me this 5-membered ring. 1, 2. Well, sorry, I didn't actually count this carbon out here. So that's 1, 2, 3, 4, 5. Where is the carbocation? On what carbon would I find the carbocation now? No. 1 had the carbocation. Remember, methyl, methyl,
Are we using
1, 1.
Are we getting the hydride group in 5?
There's no hydride
Okay.
moving. This is an alkyl shift.
Okay, got it.
It's not really a methyl shift because it's not just methyl. It's not a hydride shift because it's not just hydrogen. We call it an alkyl shift. It's this whole bonding group that's moving. 5 was bonded to 2, but now 5 is bonding to 1. That expands the size of the ring, shoots down the angle strain. Carbon 1 had the carbocation. Now it has a bond from 5. Similarly, secondary carbon had the carbocation. Now it has the hydrogen, or now it has the methyl. Oh, and I want to be so careful about this. Don't. Anybody that walked in late would see that and think, right, okay, I can just show it that way. 2. 2 lost its bond from 5. What does it get if it loses its bond? A positive charge. Now, is that the most stable carbocation possible? Especially in its adjacent vicinity? No, and so this actually goes through a second subsequent rearrangement, this time a hydride shift to get to a tertiary carbocation. 2 steps needed. We do both ring expansion and stability of the carbocation rearrangements. It's just more convoluted, and I don't have examples that really are meaningful of like when this happens or why this happens, so we don't get into it too much. But if you can understand the process of why a carbocation rearranges ever, then you can start to understand that process in a more complicated system too. All right. Elliot.
I think there was a question on, or just like, it will only, the carbocation will only ever be arranged down like one carbon.
Correct.
Like it's limited. Yeah, okay.
That's why. That's right. Do you want to know, can you explain why a carbocation can't shift more than one position away? For instance, if my carbocation is here, it doesn't move. It won't move to secondary or secondary because those are equally stable. Why is it the methyl group won't shift over there?
The charge difference isn't enough to pull it.
Not quite. Not about the charge difference. It's about orbitals. Electrons exist in orbitals, or really orbitals define the region that electrons take up. And so electrons moving requires orbitals overlapping. So it has to be adjacent. If this is my carbocation, then this would be the CH bonding electron orbital. You can notice it kind of looks like an sp3 orbital. It's got that tiny lobe on one end, but a really big lobe on the other. This is a molecular orbital. It's the sum of s and sp3. And you can see that it actually resembles the shape of the p orbital like a little bit. Squint your eyes and shake your head. It's the shape and orientation of the p orbital. So now you squeeze these close enough together. Overlap allows the electrons between C and H to shift over to this new carbon, leaving in its wake a different carbocation. So it has to be adjacent. My first time really trying to answer carbocation rearrangements was in grad school, TAing a group of students like 2 years younger than me. And they were really confused about why this was even possible. Why should bonds be able to just walk around on a molecule? And I had no idea. So I brought it back to my undergrad physical chemistry professor. And she said, remember that molecules are not stagnant. They're not these hard sticks on the board. They are wiggly, vibrating little things. And all of those vibrations in the bonds, the stretching, the bending, the wagging, it allows bonds to be a lot more flexible and movable. So with just a little bit of movement energy, that bond can shift over to something that's more stable. Okay, any other questions you guys want to review before we move on? Were there any reactions that surprised you, or confused you, or upset you? Can't do much about the upsetting. Were there any that you didn't see that you wanted to see? You?
You show the mechanism of hydroboration stuff, how it kind of works.
Actually, I won't draw the mechanism for hydroboration oxidation. That's the one you want?
Yeah.
But I will show it to you because it is interesting. We did look at the first step of hydroboration oxidation. It's a concerted mechanism. The two bonds break and the two bonds form at the same time. It has kind of this square transition state. The next step, the oxidation step, is a lot more convoluted. First of all, the reagents for this step is basic aqueous hydrogen peroxide, H2O2, H2O, NaOH. It's the basic part that's important there. It deprotonates the hydrogen peroxide, and it leaves you with this peroxide this deprotonated peroxide nucleophile. I don't know if this mechanism goes all the way, huh? Isn't that a shame? What this peroxide radical does, no, that doesn't show it either. It ends up inserting itself between the boron and the carbon. Okay, this is with an alkyne starting material instead of an alkene, but it's okay, it's very similar. We get the transition state. Wow, this is really hard. We get the transition state, yeah, where the hydrogen and the bromine are adding, and then we have the hydrogen and the bromine added syn to each other. I know that's an alkene, but imagine it's an alkane. They'd be both wedged or both dashed. Then the peroxide binds to the boron, and then what you'll see is that the carbon takes electrons away from boron and gives it to the oxygen. Then the oxygen takes electrons back. So the peroxide is essentially inserting itself between the carbon and the boron. That's what allows H and BH2 to add syn, and then the BH2 to be replaced with OH, also syn. Do you remember in the halonium ring intermediate and the halonium ring intermediate for halogenation, haloether, and halohydrin, we say that that halonium ring is attacked from the backside and it opens up to leave you with anti-addition. Two groups, opposite stereochemistries. This is not that same type of backside attack. This is more of molecular insertion. And so it preserves the stereochemistry of that first step. There's a reason why I don't ask you to show it. It's not necessarily intuitive, and I don't think that it indicates how well you understand arrow pushing. This is something you have to memorize. That's plain and simple. Another one that, quite honestly, professors do ask students to memorize. The ozonolysis mechanism, not intuitive, not easy to memorize. You'll see ozone reacts with the alkene, and it forms this 5-membered ring. And then the 5-membered ring breaks into two pieces. Notice how the two carbons of the alkene are not bonded to each other anymore. That means you have two fragments that very easily could drift apart in the medium that they are dissolved in and not react to go forward to the final product. That's another piece of this mechanism that makes it unintuitive. So that you have to fragment this carbon group and then presume that they will react again. This step is also not very intuitive. You'll notice one oxygen attacks the other carbon, the CO double bond attacks one carbon, the CO double bond breaks open. I form a different 5-membered ring. This time there's 2 oxygens versus 1 between the carbons. It doesn't even show how the reductive step plays a role here, but then these groups cleave off and you get your double bonds. Not an intuitive mechanism. Interesting. And by the time you've mastered HX addition, halogenation, acid catalyzed hydration, haloether addition, you can come back and look at these mechanisms and say, yeah, I know what those arrows are saying. And that's all you need to say. This mechanism is not intuitive, it's just interesting. So for an introductory level class, this is not a mechanism that I think shows your strength of understanding organic mechanisms. I think that, quite honestly, HX addition, X2 addition, acid catalyzed hydration, those are still challenging mechanisms. But they teach you better about chemical intuition than a mechanism like this does. If you took this class at CU Boulder, I know for a fact there's a chance a professor would ask you to show this mechanism. And I just don't get it, because I don't think that professor has this memorized either, or understood. Maybe memorized, but not necessarily understood. All right, that's my rant. Any other questions? Any other mechanisms you want to see, Yoon? Great.
Do you pick the active questions that's on the homework?
I do.
It's kind of diabolical to pick that pheromone with micro. That was like 25 carbons long.
Why?
Just sounds
It
like
was.
click, just a lot of counting.
You really close my computer screen counting little pieces.
Okay. I thought that was applicable and interesting.
It was.
That was the oxidative cleavage with KMNO4.
Yeah,
Yeah. Okay.
just a long chain.
I guess I didn't think about how long it was. I do pick them, but I don't have to solve them in order to choose them, so there is a downside there. All right, I have a new document for you, and I don't think I've uploaded it. We're going to be moving into a big unit. Actually, this unit has 3 sections, and the sections are not, oops, wrong class. The sections are not evenly distributed. So, wait, I had another one up, didn't I? I also wanted to show you statistics. 87% average on part A for this unit 4 test. That is up, I think, from a 74% average on spectroscopy, or maybe it was something higher, 79 or 81 or something. It was definitely our lowest part A average was the spectroscopy unit. We're back up. That tells me alkene addition reactions fairly well understood. Part B, 84% average. I think that's the closest part A and part B have ever been to each other. Normally, it's a bit of a larger discrepancy between the two of them. Also pretty good. I do want to point out on the mechanisms of part B, there were only a few things that I noticed throughout the class that were wrong. And I want to highlight them because they're fairly common issues. Let's say we have something like the HX addition to an alkyne here. And we know that the product looks like this. One thing I see students do is they'll try to show the formation of a product here and then also have it interact with the structure they show next. So rather than showing the intermediates reacting, they take something on this step and show it reacting with something on the next step. I want you to think about these mechanisms as snapshots, instances, while watching a molecule react. That means you can't have electron arrows that go beyond elementary steps. This is time 1. This is time 2. Nothing from time 1 exists anymore at time 2. So you can't have it attacking something at time 2. You have to start over completely. So you would show the carbocation and the halide. Rather than an arrow coming from 1 to 2, look at this new instance. I would phrase this as reinventing the wheel. If you're not taking what I've given you and essentially just copying it and applying it to the new structure you have, then you're doing something wrong. I don't want you to guess at what the mechanism would be. I want you to follow what the mechanism is and just apply it to this new structure. So don't reinvent the wheel. Follow our mechanism step by step. Show each intermediate and show how the intermediates react. Don't try to summarize. It doesn't work. It breaks the laws of physics. All right. Overall, great job on the Unit 4 test. Now, our final unit, Unit 5, we're going to be looking at alkynes, alkyl halides, and alcohols as starting materials. I have finished creating your objectives sheet. I think I am curious to check in again. Do you guys ever go to these learning objectives documents? Yeah? Can you tell me how you use them? So you what? Do you kind of use it like a checklist and say, yes, I understand that point, I understand that point?
Nice to reference throughout the unit to kind of like, sometimes week by week you can be so like tunnel visioned in on what you're learning that week that sometimes it's good to like remember like what the other parts of the unit are going to be.
Sure.
Yeah, and they were useful on the midterm too, because like they helped me remember like, oh yeah, like we talked about this. This is how long ago that was.
Details that just kind of fall through the cracks
Yeah.
otherwise?
Just the order in which we learn things in is one of the main things that I think those documents demonstrate, which is like helping me remember like I should probably go over this more because this is older material.
Good. Any other ways that you guys use this that you want to share?
I don't use them because I'm here most nights, but if I wasn't here, they would be very useful. Especially if I wasn't here and wasn't necessarily like watching your lecture and was trying to use third-party resources, it would be, I'd use them a lot in that case.
Yeah.
I think others probably do who are not in this room.
Good. Awesome. I would also say if you're thinking of making a table of reactions, this is a good resource because I'm listing all of the reactions that I'm asking you to know, separate from their mechanisms. So you have a list of all the reactions to know, also a list of all the mechanisms to know. It's not loading on my end. I don't know about you guys. I want you to notice our last unit. It's very section 9 heavy. And then section 10 light and section 11 medium. Looking at how this is going to play out over the next couple of weeks, I'm hoping that we finish up talking about alkynes and all of those reactions on that list this week. You guys got a taste for what those reactions feel like last week. It's just listing a bunch of reagents, showing what functional groups you can form, and then just applying it. But one thing we're going to be doing differently in this unit is creating a synthetic pathway, multi-step synthesis. Take this functional group, turn it into a new functional group. With that functional group, react it further to a new functional group. Multi-step synthesis sometimes leaves you in the dark for how many intermediates you need to get from starting material to product. And this is what your final analysis of an organic molecule assignment is going to be. You're going to present a plausible reaction with your starting material or a plausible reaction to make your starting material. So you'll want to look at all of the functional groups in your compound and say, do I know how to take that functional group and turn it into something? Or do I know how to make that functional group from something else? You've already got a handful of reactions you can use. We're going to learn even more reactions, and it'll be your job to predict just one step, either a retrosynthesis of your compound or a synthesis with it. Oh, I'm looking at the wrong spot. So this week, finish alkynes. Next week, talk about that section 10 on organohalides, which is very small, and kind of just gets us into semantics. And wrap up anything on alkynes that we need to. Thanksgiving break is off. And then we'll talk about our last set of reactions before the unit test. A reminder that after our last unit test, we have a week of review. And that is not material I prepare. That's material for you. On this Monday, I'll open up a new Canvas quiz that has all of the questions from all of your unit tests so that you can go through and see all of those topics again. It has like hundreds of questions, but that's better than having less. And then you also have your practice final. And this whole week is for you to come and ask questions and prepare for the final. So that's our game plan. Let's dive in. We're actually going to start with what's on the top of this worksheet, which is nomenclature of alkynes. When we look at nomenclature, we see alkynes show up in the suffix. That's how we know an alkyne is present. Alkynes have a lower priority than alcohols. And we're going to talk about the nomenclature of alcohols again when we get to that section 11. They have an equal priority with alkenes. So I want to dive in a little bit. What if we have both an alkene and an alkyne in the compound? Both of them need to be designated in the suffix, but who do we prioritize? If they have equal priority, how do I know whether to prioritize the alkene or the alkyne? Go for the lowest locant. Whether that gives the lowest locant to the alkene or whether that gives the lowest locant to the alkyne, go for either lowest locant. And then the trouble? What happens if they have the same locant in either direction? What do we do if tied? Alphabetical. What comes first? Een or ein? Een. Remember, these will be put into the suffix as een, ein. So we go alphabetical and we give the lowest to the een of the een, ein. Okay? Oh, and actually, let's fill this in. What priority comes after alcohols, alkene, alkynes? What groups do we look at after that? Yeah, alkanes, alkyl groups, and those halogens. Okay, granted, the halogens don't show up in the suffix. But when looking at a lowest locant set, if everything else is tied and it makes no difference, then you can look at a difference between the alkyl groups and the halogens. Why don't we take 8 minutes, work on naming these structures as drawn and drawing these structures as named. Feel free to work in groups. And at 5:45, we will move on to look at preparation and reactivity. question. I'm going to point it out to the class. Hey guys, let's talk about this first carbon, or this first compound, because identifying alkynes can be tricky. Remember we said every end and every bend is a carbon, but alkynes don't bend, right? Alkynes are sp linear carbons, which means I'm looking for the end. Here's the end of a triple bond, here's the end of a triple bond. That means there's a carbon here and a carbon here. If it helps you, sketch in those carbons, just like you did at the beginning of the semester when you were learning bond line structure. Just draw in those carbons so that you can see them a little bit more easily and count your carbons. Yeah. E9. Exactly. Feels weird, right? Although, never make it a terbutyl group if it can be counted as part of the longest chain. Yep, you got it. That's cool. But you can take one time and draw it not as a zigzag through the empty carbon, but draw it as linear.
Yeah, that,
Or since you've already got the zigzag, oh, I was going to say, I'll take that part. Since you already have this zigzag, I was going to say it can go straight out of that zigzag. Be kind of like this. Here's the zigzag, and then once you get to the alkyne, just go straight
can't
through
you do
it.
1, 1, 3?
No. Zigzag all the way through these carbons, and then the alkyne is not at the zigzag. The alkyne is linear.
What did you say? Can't you do 2, 2, 3?
Kind of. Why don't you redraw what you had before? I want you to keep what you had as a reference. I'm not going to mark it off. I just wanted to. Yes. Yes. Oh, okay, okay. That's exactly what it's like. So the carbon-carbon triple bond feeds into a bond straight out of it. That's what you got. Good job.
Okay, yeah, but
Same thing, yeah.
can't you
Instead of zigzag, that's not its orientation. It's a linear. Here it works. If it's any consolation, I look back at my OCHN 2 notes not too long ago, and I drew my alkynes with zigzags. Just force it out. It's not horribly incorrect. It's just not prioritizing the placement of the alkene or the alkyne. Well, then how can it be 2 dimethyl? And if it's dimethyl, then it should be 2 locants, 1 for each locan. And, sorry, I'm going to name the suffix ene, E-N-Y-N, alphabetical. So you've added an ine and an e, and then you just put a locant, yep, in front of ene and in front of ine. And remember, we only number 1 carbon of the alkene and 1 carbon of the alkyne. We assume that you count through to the second carbon. So you just need 1. You have not prioritized your alkene or your alkyne. Yes, great job. its suffix becomes enine. You see that in red? And you can put a locant. You can put a locant before ene. You can put a locant before ine. Well, you actually put hex, and then you kind of turned that into your ene. Sure, it wouldn't be possible for that to happen, but I like what you're saying. And we actually dropped the E off of ene because we're going to stopper it with another suffix. So the ein kind of acts like a suffix stopper to the E. So like just so, like we have on the board in red, on the bottom right, ein, ein, no second E. It's good. Now Sarah, are you starting to count your carbon chain at this carbon? Yeah, we should always count through an alkene. Oh, and I think you counted this carbon twice. You counted it once on top and then once on bottom. 1, 2, 3, 4. Good. You had the right number, but you had doubled up on one of them. Hey, if you haven't already, try drawing one. Good job. Now, can you draw your alkynes linear? You keep what you have as a reference. But good. Alkynes have linear geometry. They don't have zigzag bond lines. So keep what you have as a reference if you want to. But now see if you can redraw it. Yeah. Oh, Lord. Should have been hex. Can you put hex and make it hex? All right, I have one name to fix, by the way. As it's named, it's not named correctly.
At least we realized it now.
Yeah, right. Great job. Well, it kind of looks like you're making the carbon on the ring carbon. Do you agree? So we want the carbon on the ring to come off. And also, this is not even what you draw the second hex. So you'll need one extra bond. And you, I want this to be hex. You drew it as hex. Oh yeah, I did. It's actually not a die. Oh, it's an aldehyde. So yeah, you need one extra carbon in the chain. And if you can, straighten it too. Kind of like you did here. Yep.
Well, chemistry doesn't, so sorry. The electrons are not going to be happy with you today, sorry.
No, you're just 4. Focus 3.
Because the electron in carbon
You counted that as carbon of the alkyne, but it can't be, right? Carbon's in the ring, not the carbons of the chain. All right, should we go through them together? All right. Structure number 1. What is my parent chain? Hexyne. E9.
There's a Y in my head.
So we've got hexyne. Should I number this from the left to the right or from the right to the left? Why should I number right to left?
There's a mess coming off of 2.
I want to prioritize the alkyne though. Either way I number, the alkyne is at position 3. So no matter what, this is 3-hexyne or hex 3-ine. But it's tied, so then I look down at my alkyl group and I give the lowest locant set for my alkyl group. 2-methyl, 3-hexyne. Again, another way to write this, 2-methyl, hex 3-ine. Technically, IUPAC only accepts this, but IUPAC is a bunch of little wimps, and they let people walk all over them. Don't. I'm kidding. That is all in good humor. IUPAC would have laughed at that. All right, let's draw 1-butyne. How long should my carbon chain be? How many carbons? 4. And the alkyne stretches between carbon 1 and carbon. Right, we're always assuming that it's the next carbon that the alkene or the alkyne are connected with. So here's a 4-carbon chain. Here's carbon 1, and so here's my alkyne. All right, now I'll do my best not to take points off for that if that's what you give me, but sometimes students aren't super clear about their bonding, and so I get a lot of structures that look like this. Now, me, someone who's been doing this too long, I know that that is the end of a triple bond. That's a carbon. Carbon, carbon, carbon. This structure has 5 carbons according to my eye, but to the chemist student, that's just a part of the zigzag. So we have to try and avoid having this carbon of the alkyne not meet all of its bonds. One way you can do that is you can have these triple bonds feed right into the line. It looks really ugly, but you might think alkynes look ugly anyways. However, this still isn't obeying the true geometry of the alkyne. The alkyne is linear. This bond comes off at a 90-degree angle, not 180 degrees. So there's a few things that you can do. If you've drawn your zigzag and then you draw your triple bond and you recognize it's not straight, you can take that triple bond and rotate it so that it does connect to the other group straight. And you'll notice that when you draw a triple bond, sometimes the end of that position is a lot more clear than when it's drawn by the computer. You can see where my triple bond ends and where my single bond starts. That makes it a little bit easier. Or another way you can draw this correctly is you can start with the triple bond, and instead of a zigzag out, have a group come straight out from there, and then draw the rest of your bond line structure. It is a challenge. I was telling them in the back that when I took OCHEM 2, we actually started our semester with OCHEM 2 with alkynes. I drew mine in zigzag, and it never even crossed my mind that I was drawing their geometry wrong. But we understand the structure better when we show it appropriately. Okay, my next compound. Let's name it. This time I have an ene and an ine, which means my suffix is going to have ene-ine. And remember when we stopper our suffixes, we said that alcohols stopper the suffix with OL. That means we drop the E and we add OL. I'm basically stoppering alkene with alkyne. So I drop the E of the ene and I add the ine. I want to prioritize either the alkene or the alkyne. So which direction should I start from? From the left, where the alkyne is at position 1. If I numbered this from the right, My alkene would have been at position 3. That is not the lowest locant set for the alkyne or the alkene. One important thing to point out, that does look like a tert-butyl group. We could talk about it as a tert-butyl group, but it does add to the longest possible parent chain, so we will count it instead as 2 methyls coming off of the parent chain. So I have 5,5-dimethyl. Why is it not just 5-dimethyl? There are 2 methyl groups. It doesn't matter that they come off of the same position. There are 2 of them. They should both get a number. 5,5-dimethyl. It could have been 4,5-dimethyl, 3,5-dimethyl. That would have changed it significantly. Hex. Now, my ene comes first, and the alkene starts at position 3. So hex 3-ene. And then my alkyne, which is at position 1. Can I assume my alkyne is at position 1 and call this 5,5-dimethyl hex 3-ene-ine? Or do I need to say 1-ine? We're not in a ring. And when you're not in a ring, you always have to explicitly say where that position is on the carbon chain. And sometimes even in a ring, it's best to say explicitly where that other position is. Okay, there is another way we can write this, which is 5,5-dimethyl, 3-hexene, 1-ine. I cannot pull both locants out front. I can only pull one locant out front. So whatever locant describes the first thing in the suffix, that can be pulled out front, but otherwise it's best, and this is why IUPAC honestly does have the right idea, it's best to just put your locant right in front of the indicator of that functional group, right in front of its suffix. All right, let's draw the next one. 2-butyne compared to 1-butyne. 1-butyne had this 4-carbon chain, and the alkyne was at the end. 2-butyne is a 4-carbon chain with the alkene in the middle. What I noticed a lot of people doing with this one was they took carbon 1 and they made it a carbon of the phenyl group. But you can't count a carbon in a ring as part of a chain. Those have to be completely separate. So off of position 1, I add a phenyl group. You could draw phenyl, or you could just write pH. Did it matter which carbon I chose to be carbon 1? Sorry? Yeah, 2-butyne is perfectly symmetrical, so either carbon would have been carbon 1. All right, my last nomenclature. This time, do I number starting from the alkyne or starting from the alkene? Raise your hand for alkyne. Oh, raise your hand for alkene. Tell me why. Good. Tied locant set for the position of the alkene and the alkyne. It's not a tied locant set for the bromine. The bromine could be on position 1 or position 5, depending on how we number this, but it's a tied locant set. It's either 1 alkene, 4 alkyne, or 1 alkyne, 4 alkene. If it's a tie for the same priority, I go alphabetically. Alkene comes first, alkene goes in the name first. So I get 1 bromo, hint 1 ene, 4 ine, and there is a piece of information I should have added to both this one and the last one.
Hold on. Z Z, and then E.
Yeah.
Is
Which one should get what? What should I put in blue? E or Z?
E.
This is a trans alkene, so I should communicate that in its name by having, oops, that's the wrong color. By having E written in front of the name. That tells me how the alkene is configured in space. And for this one on the right, also E. Z. Bromine and the methyl group are the high priority. So this gets Z, 1 bromo, pint, 1 ene, 4 ine. Are alkynes ever stereocenters? We said chiral carbons can be R or S. And alkenes can sometimes be E or Z. Can alkynes ever be a stereocenter? No. The most you can ever get out of an alkyne is a more substituted carbon and a less substituted carbon. More substituted, less substituted.
Kind of running out of carbons to do anything.
All right, let's draw our last one. Remember, I said this one was pent, but we need this to be hex in order for it to be right. No, we want the lowest locant set for either the alkyne or the alkene. And in this case, it was a lower locant set for either one. They both started at 1. If it's a tie, then I go alphabetically for the alkene, since alkene comes before ine. So it actually had nothing to do with the bromine. The bromine ended up on position 1 out of pure luck. Alphabetical luck between alkene and alkyne. You're welcome. If we left this as pent, the name that I had would have been totally wrong. So this is supposed to be hex. Now remember, I recommended last time when drawing that you draw the triple bond first and then have your straight lines come out of that triple bond so that you know your alkyne is linear. That's only 4 carbons. So I'll add 1 on one side, 1 on the other, and now I've got a 3-ine group. Hex 3-ine. Now you can see that this is also suffix stoppered with -one, specifically dione. So position 2, a ketone, and position 5, a ketone. I'm not going to ask you to draw structures with an -one suffix. I'm not going to ask you to name structures with an -one suffix, but I did want to put a challenge in there to remind you guys, you know a lot more about nomenclature than what we're needing to cover in this course. It's not any more challenging. It's just a little bit more unique. Any questions?
Can E and Z apply to alkynes as well? Like if you had that ketone flip the other way, and so the carbons coming off of it are the same. You see what I'm saying?
Yes and no.
Okay.
This does have a conformational isomer, but that's just rotating around a sigma bond. That's the same as unit 2, when we talked about conformations rotating. All I've done is rotated around a sigma bond. So no stereochemistry change, just perspective change. But there is something I want to talk about, which is symmetric, asymmetric, and unsymmetric. Okay, I'll be honest, I don't know that these words are in any textbook, or if unsymmetric is an appropriate term. But I do want to talk to you guys about what they can mean to help you distinguish between alkynes. A symmetric alkyne has the same R groups on either side. So, for instance, 2-butyne is symmetric. Acetylene. And I'm going to actually put this one's name because this is an important chemical. I don't know if you guys remember this, but back in section 6, we talked about types of organic solvents, and we looked at things like acetone and acetic acid and ethyl acetate, and they all shared this ACET prefix. Do you remember what that indicated about the chemical? It usually means a 2-carbon carbonyl compound. Acetyl chloride, acetaldehyde, acetonitrile, acetone, ethyl acetate, acetic acid. They all have a 2-carbon group with a carbonyl, more or less. And you'll notice that this is also a 2-carbon group, but definitely no carbonyl, and definitely no alkene. Why do they call it acetylene? If anything, they could have called it acetylene, and they could have put a Y-N-E in there. It's terrible. Also, you can write acetylene with a little bit more detail so that it doesn't just look like these 3 lines on the board. Has anybody ever used acetylene or know someone that uses acetylene? What for? Welding. Yeah. Acetylene is a really common fuel. It burns really hot. Acetylene was originally used by miners. This is a fun story, sorry. Miners would harvest calcium carbide, CaC2. That's calcium 2+, and this diacetylide ion, C2, 2-. And they would mix this with water. They'd have this little compartment on their hats, and the calcium carbide would sit in the bottom, and on top was a little screw. They could unscrew it a little bit, and this water reservoir above that calcium carbide would slowly drip in. When calcium carbide reacts with water, it produces calcium oxide and acetylene, and the acetylene gas escapes out from a little hole inside of that helmet, and then they light it, and they get a fire on their helmet. So this was pre-electricity, pre-flashlights. If you didn't want to carry around a lantern and you wanted that light fixed on your head, get a compartment of calcium carbide, drip some water on it, let the gas escape, and light it. And you've got a burning flame on your head. Wouldn't recommend it anymore. Okay, acetylene, great example of a symmetric anhydride. An asymmetric anhydride is where one R group does not match the other R group. We can write this as R and R prime. This would be something like 2-pentyne. On one side is a methyl group, on one side is an ethyl group. Those are not the same. Or like we just drew before, 1-phenyl butine. And we could have something like 1-butyne. 1-butyne is also asymmetric. R is H, R prime is ethyl. And then this gets us into this idea of unsymmetric. Not just having different carbon groups, but having different degrees of substitution. So this 1-butyne is a good example. But truly, any time that you have a carbon on one side that is not bonded to anything else, and then the other carbon has a bond to another group. In fact, this idea of unsymmetric has another name. We call them terminal alkynes. A terminal alkyne has a carbon chain on one side and a hydrogen on the other. If you were to describe the other type of substitution, not a terminal alkyne, but one that has carbon chains on both sides, what would you call it? Intermediate? Not a bad guess. We call them internal alkynes. They sit within the carbon chain. So we'll be working with alkynes that are symmetric, alkynes that are asymmetric, and specifically some asymmetric alkynes that are terminal alkynes, unsymmetric in terms of the degree of saturation, the degree of substitution of their carbons. All right, let's take a 5-minute break. 6:15. Let's come back. We're gonna look at preparation of these alkynes.
Wait, is the bottom one in the asymmetric row? Is it in the unsymmetric group as well, or is it also asymmetric?
Isn't it both?
Okay. That's what I was confused about. I don't know, man. I have that one thing from Chipotle I always use. It's so bad. I can't get it right.
Just before the final exam. That's its new
Actually,
tradition.
I wish I wasn't crack cocaine addicted to it because the order that I get specifically, like I always tell people that are from Chipotle, like if you haven't like found your very yes, it's probably why. Yeah. Yeah, I eat it nachos. I always eat it. I always eat my full nachos. That's why I don't always eat a full because I don't always want to get the extra fat. No, that's what I'm saying. I do when I want to. Like I don't always do it though. I'll always just get like sometimes I'll get the burrito. Sometimes like the burrito is like the tortilla is not that much. Sometimes I'll get the bowl and I'll just get it with the fork. Okay, that has happened to me once. That has not happened to me in a very long time. Yeah, I think you just from what I can tell you right now, that sounds like did you go to the same Chipotle twice on that night? No. Because from what it sounds like, when I have seen this happen, either I don't have the new one. Whenever I've seen this happen, it was like some new employee that didn't know how to pack the burrito properly, and when you take a bite, the bottom's out. The bottom's out when you take the bite.
All right.
You have to like.
When we learned about alkenes, we said that we can prepare alkenes by elimination reactions. Take some sort of leaving group, like a halogen typically, and a hydrogen from a beta position, remove those two groups and unsaturate the molecule. That creates an alkene. How could we do something similar to produce an alkyne? Would the same idea work of taking one hydrogen and one other group, like a halogen, away? Could I create an alkyne? How many degrees of unsaturation in an alkene? 1. How many degrees of unsaturation in an alkyne? 2. Which means not one elimination reaction is needed. 2 elimination reactions are needed. So I need 2 leaving groups and 2 hydrogens. In the same way, we still use a strong base. It's true that we would need twice as many equivalences of that strong base, although oftentimes you just run this in excess anyways. And that eliminates both of those groups, creates 2 degrees of unsaturation. When this is a halogen, this X group is a halogen, we refer to this as a geminal dihalide. You remember why we call it geminal? They're twin halogens. They're on the same carbon. I'm not sure which chemist was into astrology and liked the overlap, or maybe it has nothing to do with that. I don't know. Do you suspect we need to have a geminal dihalide in order to form the 2 equivalences of unsaturation between these 2 carbons? Is there any other structural rearrangement that I could have that would lead to the same product? Do you want to try and describe it? I have a halogen here and a halogen here, and a hydrogen on both. How would we describe this dihalide? Vicinal. Vicinal comes from the word for vicinity. And in the presence of that base, it forms the same alkene. Sorry? Alkyne. All right, so now we've got this activity. What alkynes can be made And what could have made these alkynes? This question here is a synthesis question. What can I create from what I'm given? This question is considered retrosynthesis. From what I'm given, how can I get there? By the way, any of you that really like downloading the learning objectives list, I did forget a reaction. I thought about it today, so we're going to have to put it, I'm going to have to add it to the learning objectives list and re-upload it. All right. In the same way that we did this with alkenes, we can identify the alpha carbon, although now it's important that we identify at least one and up to two alpha carbons. For instance, here's alpha, here's beta, and we made our alpha beta double unsaturated. But then here is alpha and beta in red, and then the same alpha and beta in blue, but swapped. Because one of these halogens takes the opposite hydrogen. So I can look for a geminal alpha, or I need to look for two vicinal alphas. Deal? A geminal alpha with one beta, or two vicinal alphas and betas. Let's take a look at this first one. Also, IUPAC name for this is so fun. It's 1,1-dibromoethyl cyclopentane. This whole thing is a substituent of the longest parent chain, cyclopentane. 1,1-dibromoethyl cyclopentane. Where's my alpha carbon? Is it a geminal alpha, or do I need to look for two vicinal alphas? Geminal alpha. And it's a secondary alpha, which means I've technically got two beta positions. So I need to be careful about structural isomers that could be possible. Let's consider this blue beta on the right and this green beta on the left. Is it true that I need my geminal beta carbon, if you will, to have two hydrogens in order to eliminate to form an alkyne? Yeah. I've got two leaving groups, I need two hydrogens. Do both of these beta positions have two hydrogens to give away? No. Which means they can't both form alkynes. To clarify that, if we tried to take from this tertiary carbon, see anything wrong with that structure? Nicole, what is it? 5 bonds to carbon. Five bonds? Well, first of all, that means that we removed a hydrogen that wasn't even there. And because we removed a hydrogen that wasn't there, we broke the octet rule for the carbon. So not even feasible for us to do it. All right, so let's look at the alkyne that forms when we eliminate from the position on the right. Alpha, beta, here's alpha, here's beta, triple bond. Terminal alkyne or internal alkyne? Terminal. It runs to the end of the carbon chain. It has a hydrogen attached to one position. There's the alkyne that can be made. By the way, when a carbon has 5 bonds, they call it a Texas carbon because everything is bigger in Texas. And they have been reported. They're very highly strained, high energy complexes.
I'm assuming they don't like to use this.
They don't like to use this. All right, my second structure, geminal or vicinal dihalide. How many possibilities for an alkyne do I have? Just one. Because now I have to make sure the alkyne goes between those two carbons. Now, if it helps you, let's map our carbons so that this carbon chain doesn't get away from us. We don't add too many or too few. I'm going to start at the aldehyde. 1, 2, 3, 4, 5, 6. I should have a 6 carbon chain. Alkene, or the alkyne should be between. Three and 4. I come down and map it. Terminal or internal? Symmetric or asymmetric internal? Asymmetric. Got a carbonyl on one side of that carbon chain, no carbonyl on the other. That's my only alkyne possible. That's the only alkyne that will form. All right, my last one. Geminal or vicinal dihalide, which means I need to consider 2 possibilities. And this time, they really are 2 possibilities. I have 2 hydrogens on both of those beta positions, and they're different alkyne structures if they form. It's not like you form either one and it's a symmetric alkyne. These would be structural isomers. Can you predict the 2 alkyne structural isomers that form here? Map your carbons if it helps. Number them in the starting material and then use them to keep track of where the alkyne goes in the product. Yep. Went too far away on this side. Oh, actually, got the log like that here. So I'm saying this is carbon, this is carbon. That would be a turn this way. So here's carbon 1, 2, 3. 1, 2, 3, great. But now I want the other side. I am between them against 3 and 4. Good work. All right. How did mapping work? Was numbering the positions and then mapping them to the alkyne easier than just guessing and checking? So let's say that this is position 1, 2, 3, 4, 5. I want to show an alkyne between carbons 1 and 2, because 2 is my alpha, 1 is one of the betas. I also want to show an alkyne between 2 and 3. So here's my alkyne. If this is carbon 1, 2, 3, 4, 5, and then my other alkyne, this is carbons 2 and 3. So then here is my nitrile group, the cyanide, and then 4 and 5.
We're counting those carbons. Are we ignoring the one bonded to the nitrogen?
I ignored it, but this is mapping. And mapping, you can do whatever you want to. I could have started at the cyanide carbon. I could have started on the right-hand side of the molecule. When you map, it is not the same as nomenclature. So you are just assigning symbols to keep placeholders for your atoms. If you don't like the numbers, draw in shapes. If shapes are weird, use colors. Whatever helps you keep track of the carbon positions. All right, now let's do a retrosynthesis. For these two alkynes, can we come up with structures that would produce them? And preferably, structures that would produce them as the predominant alkyne. So come up with a dihalide for both of these alkynes that could be eliminated to form these. Retrosynthesize to what dihalide precursor is needed. Think about mapping. Think about whether you want geminal dihalide or vicinal. Guess and check.
Is either of those better? This one could form another isomer too. Yep. Good, good. Great. Are there any others? Impossible. Yeah. This one's reversed because it only forms that ester. Yep. That's great.
We must have like insane people with people
This,
who are taking this
that's
class.
perfect. That's it.
Like, what are they talking about? These entirely different languages.
You were doing the, no, that's vicinal. Yep. And vicinal, it does sound like it ends with YL, but it actually ends with AL. But that's it, and that's the best one. What? Now, are any of these better or worse? Is your review still up?
The
Yeah.
one.
Vicinal, yes. But which is the best if this is the only isomer you want to make? Is it? Because this could form an alkyne between 2 and 3 and 3.
Oh yeah.
That's right. This molecule. So this is, that's the best. This one was, I would say, would be a second best because it actually can't form an alkyne. Yes. Oh, this is the vicinal. Good.
feel like then you could say like then it would form. And you could say and the other side is the Are you saying?
So you've mapped your carbons, which is the best start. And you know that you want to have 2 hydrogens, 2 halogens leave from carbons 3 and 4. But it doesn't matter where you put them.
You're right. That's totally
So
right.
Sarah gave an example where she did a vicinal dihalide. 1 carbon had 1 halogen each. That's the best one because the vicinal always has to form between the 2 carbons. So it'll always be this isomer. But there are geminal isomers that work as well. Good work. All right, let's go through these. I noticed a lot of you numbered your carbons. Great job. Now you know that in your starting chain, between positions 3 and 4, you need to have either a vicinal dihalide or a geminal dihalide. So there's a lot of possibilities. One of them is to have a dihalide that is vicinal, 1 on 3, 1 on 4, and the alkyne can only form between carbons 3 and 4. That would be the best one for forming this product, because that's the only product that can form. But if you had a geminal structure on either 3 or 4, this alkyne is a product, but it might not be the only product that you make. If you actually had it on the carbon closer to the tertiary carbon, this is still a predominant product because it can't form an alkyne to the right. There aren't 2 hydrogens to remove. So this would be a good second, a good backup. With 1-butyne, we had to draw this out in order to predict possible starting materials. And once again, I have 2 that are great, only form this alkyne, and 1 that is not so great. Now this time I want to show you guys with actual halides. So let's say I've got a dibromo. 1,1-dibromobutane only forms this alkyne. Geminal dihalide, but there's only 1 beta position. 1,2-dibromobutane, vicinal dihalide. Once again, only 1 alkyne that can form. It's going to be the terminal alkyne. And then we have 2,2-dibromobutane. This would be the worst starting material for this alkyne because it could form the terminal alkyne, but it might just form the internal alkyne. So this would be a second up. These would be number 1. How's that sound? Great. All right. The next thing on our worksheet actually deviates us away from looking at reactions. And I think this is probably for the best. We'll save reactions for Wednesday, and we'll round out today's lecture with talking about this ranking of stability. This unit has a lot of reactions that involve radicals. This is terrible, sorry. Just for a glimpse, we are going to be repeating a lot of the same reagents that we had in alkene addition reactions, and we'll be doing addition reactions to alkynes, HX, except now that we have 2 equivalences of pi bonds, I can do 2 equivalences of addition. So when we do HX addition, we're going to look at 1 equivalence of addition and 2 equivalents of addition, consuming 1 pi bond or both pi bonds. Halogenation, 1 equivalence and 2 equivalences. Oxymercuration and hydroboration oxidation, only 1 equivalence. And it will surprise you what the hydrate products actually are. The hydration products are not alcohols like they were with alkenes. Oxidative cleavage, 1 equivalence. We can do full hydrogenation, 2 equivalences of hydrogen, or partial hydrogenation, 1 equivalence of hydrogen. And there are 2 different forms that we want to look at because there are 2 different impacts that these reactions have. This metal in ammonia is a radical reaction. We're going to be using a metal like lithium or sodium. Elemental lithium and elemental sodium have the same number of valence electrons. Do you guys know how many valence electrons in sodium and lithium? 1. So as a 1 electron element, they can only give 1 electron. That's going to create a radical intermediate in that reaction. And that segues us into more reactions with radicals. So we're also going to be looking at anti-Markovnikov HX addition. To be fair, maybe this should have gone in section 8 with the alkenes, but the textbook kind of rolls it in with radicals. So we saw that we could add HX Markovnikov. Now we'll be able to add HX anti-Markovnikov. We'll get regio control over our chemistry. Then we're going to do radical halogenation of alkanes, radical halogenation of alkenes, before we get into some other reactions that are quite a bit different from alkenes and alkynes. This is actually where I need to add an additional reaction, probably up at the top. We're going to look at alkynes being alkylated. We're going to add alkyl groups to alkynes. That's where we take a terminal alkyne and we make it a nucleophile so that it can attack a different group and do substitution. And that substitution alkylates it. It now adds on a new alkyl group. So that's where we're headed with reactions. And because of that, it's important that we have a look at radicals and that we learn how to rank these radicals by their stability. Now there is a nice trick about radicals, and that is that they trend with carbocation stability. Can you recall the stability of carbocations? Which way is stability tending towards? More stable to the right or less stable to the right? More stable? Why? What makes these carbons lacking an octet, these carbons holding a positive charge, more stable than these? Resonance is a big one. Is that what you said, Yoon? Here, I start to see resonance play an effect. In fact, this primary allylic and primary benzylic are more stable than even a tertiary or secondary alkyl carbocation. But before resonance, stability is based on? We go by substitution. But if you were to really define it, it's based on something called hyperconjugation. It's that moral support theory, right? Which is more electron groups surrounding this positively charged carbon can swarm that positive charge with its electrons, stabilizing the positive charge, making it less positive, less reactive, more stable, lower energy. So now we get the same trend for our carbon radicals. And I know that's really hard to tell what's just a scribble and what's a dot, but there's a radical on each of these structures. A radical, remember, is an unpaired electron, not a lone pair of electrons, a lone electron. And you can't assume radicals. You have to draw radicals. We can assume lone pairs. We don't assume radicals. So, Yoon, since you brought up resonance up here, do you think that this really has that same trend? Resonance on the right and substitution on the left? Is there resonance in these systems? I wouldn't have you guys copy all that down if it wasn't in the right order, but I want you to debate. Do you think that there is resonance with radicals in the same way that there is resonance with positive charges? Maybe. And let's not forget that Lewis structures fail to tell us the whole story of a molecule. If we were to pick this allylic system, and we were to draw the MO diagram for it, we have 3 p orbitals, which means that I should get 3 pi molecular orbitals. And those orbitals look at the lowest energy, all in phase, at the highest energy, all out of phase, and in the intermediate energy, there's a node that lies right over the central atom. So only the 2 atoms on the exterior are actually enveloped in that electron orbital. If we're dealing with this red situation up top, how many pi electrons would feed into this pi molecular orbital? There's 2 pi electrons in the pi bond, and then there is an empty p orbital. So I would fill in 2 pi electrons. And the empty positive charge, that's this orbital. That's the lowest unoccupied molecular orbital. That's where electrons will go if they come into the system. And where is it? Delocalized. That positive charge is not on the left. It's not on the right. It's on both of them at the same time. Your Lewis structure says, well, it can be on the left, and then we can move arrows, and then it can be on the right. But that's not what MO theory says. MO theory says if both can exist, both exist at the same time. Now let's consider this. What we have to assume, this is a bit of a jump, we have to assume that this radical electron is held in a p orbital. That's the only way that resonance can be allowed. And if resonance is holding this in a p orbital, then where does it go in this MO diagram? This is already taken. I have 2 pi electrons. That means it needs to go up into this orbital. So where is it? On the carbon on the right or the carbon on the left? It's in both. That radical is delocalized. So how do you stabilize a positive charge? You spread it out. You make it so that not one carbon has a positive charge, but many carbons share a positive charge. How do you stabilize a radical? You delocalize it. You make it so that not one carbon has an unpaired electron, but many carbons are sharing an unpaired electron. How would we draw arrows for this? To show arrows for the movement of the positive charge, I just show the pi electrons moving. To show movement of the radical electron, this carbon has this electron. It can share it, but it can't lose it. It's not going to toss it anywhere. It shares it with the carbon on the left. Notice that when we show one electron moving, we use a half arrow. Full arrow, 2 electrons, 2 hooks. 1 electron, half arrow, 1 hook. And then the pi bond splits apart. 2 electrons in 2 different directions. So we're showing this radical moving to this other position, and it takes 3 arrows to get there. That's Lewis structure showing movement. Whereas MO theory says it's not moving at all. It's there all the time. Oh, man. All right. So the point here is predict the most stable radical that can form on these structures. If there's more than one, show all of them. And if there are allylic radicals, radicals that form adjacent to alkenes, then show both resonance forms of the allylic radical. That's where we're going to pick up on Wednesday. We'll draw all of those radicals that are possible on those 2 structures, and then we'll dive into our alkene reactions. Have a good night, guys.